another video. And this video will cover chapter 2, globe, latitudes and longitudes, or you can call it longitudes as well, from class 6 geography. Now this chapter is going to be really tough. It's very complicated for both you and me as well. For me because it's really hard to explain all these things, and for you because you might find it hard to learn all these things. To imagine all the things that I'm trying to explain to you, to comprehend all that. So without further waste of time, let's just start. In the previous chapter, you have read that our planet Earth is not a sphere. Okay, like strictly speaking, it is a sphere, but strictly speaking, it is not a sphere, but in a loose sense, it is kind of a sphere. It is spherical, but not exactly a sphere. It is slightly flattened at the north and south poles and bulge in the middle. Okay, can you imagine how it looks? You may look at a globe carefully in your classroom to get an idea. Globe is the true model miniature of the Earth. So to give an idea, basically this is the shape of the Earth, except that this area, this area is slightly towards the outside because they said, that the center is outside a little bit. So yeah, basically that. Yeah, it's kind of like this. The shape is a little bit bulged outside. So basically, this is the shape of the Earth. See, this is, I mean, it's not completely flat at the ends. I made it a little bit too flat because I really didn't know how to properly use this app. But this will give you enough idea of how Earth is. So this is our North Pole. This here is our North Pole. This here is our South Pole. And at these poles, the Earth is slightly flat. And this is our middle part. Basically, this is a little bit bulged out. So this is how our Earth kind of looks. We can make it this point a little bit out as well, like not so out but still a bit out, and same goes for here. You can take this a bit out as well. So this is kind of how Earth looks. One more thing to note here is that the Earth is not standing exactly like this. The Earth is slightly tilted. Okay, this is Earth and it's slightly tilted, like in this angle. This is how Earth is in the atmosphere or in the space. This is the position of the Earth. It is not standing exactly straight, like it is not standing straight like this. It is slightly tilted. And what is the angle of this tilt? So you should write this as a note. This will be your first note. So write down axial tilt. This is called Earth's axial tilt. Axial tilt is equal to 23.5 degrees. Okay, so the Earth is tilted at an angle of 23.5 degrees. Okay, so now we'll start from this point here, from here. You will notice that a needle is fixed through the globe in a tilted manner, which is called its axis. So what does the axis do? The axis is basically an imaginary line that passes through the Earth's poles and divides it into two halves, two equal halves, and obviously two equal halves. 2 points on the globe through which the needle passes are two poles, the North Pole and South Pole. The globe can be moved around this needle from west to east just as the Earth moves. So we also know the direction of the move, the rotation of the Earth, right? It is from west to east. But remember, there is a major difference. The real Earth has no such needle. It moves around its axis, which is an imaginary line. So the Earth basically moves around its axis, which is an imaginary line. Another imaginary line, okay, we'll read about that later. First, let me show you what axis is. So this is our Earth's model. Now the Earth is slightly tilted. Okay, you get that point that the Earth is slightly tilted, right? So if this is the plane, this down here, so this is the plane. Our for our reference point, this is flat area or our plane. So this pole here, this pole would form a 90-degree angle with Earth. Okay, but as you can clearly see that this pole does not, or this line does not divide the Earth into two equal halves. It is passing through the middle of the Earth, but not through the center of it. Okay, there's a difference. So middle basically means like beach may say or par, yar par. But from when we talk about center, it means the exact center, like divided into two equal halves. but this is the Earth's axis. So the Earth's axis is also tilted. Since the Earth is tilted, so axis is also naturally tilted at a 23.5-degree angle. And axis is basically an imaginary line which passes through this here is the north pole here, which passes through the north pole and the south pole of the Earth and divides it into two equal halves. Okay, this is our Earth's axis, and the Earth rotates on its axis. Okay, so the Earth is always rotating at a slightly tilted angle. So get what I'm trying to say now? That if we pass a pole at 90-degree angle of the Earth, then it would not divide it into two equal halves. It would run through the Earth at some different points. But if we divide it through its axis, then this would divide the Earth into two equal halves. And the angle that the Earth's axis and the straight 90-degree pole make is 23.5 degree, and that is why the Earth's axial tilt is 23.5 degrees. I hope you get what I'm trying to say. It's not that hard either. So moving on, another imaginary line running on the globe divides it into two equal parts. Okay, now we just read about a line, an imaginary line that divides the Earth into two equal parts, and then again they're saying that there's an imaginary line running through the globe that divides into two equal parts. So what does this mean? Now they're saying that this is known as the equator. So the previous one was axis, now this is equator, and both are imaginary lines and both dividing the Earth into two equal parts. So what's the difference between the axis and the equator? So the major difference, or the only difference probably you can say, between the Earth, between the axis and the equator is that the equator is actually a horizontal kind of line, or you can say that the equator divides the Earth into two equal halves horizontally. So sorry, this line is the equator, not these ones. This is our equator. Again, this is an imaginary line. In a real Earth, there are obviously no such lines. What did I just do? Yeah, so basically this is your equator. It's dividing the upper Earth and the below and the lower Earth both into completely exactly equal parts. Now this is not a vertical division. This is a horizontal division, right? So this is the difference between equator and axis. Axis divides the Earth into two equal halves vertically, and equator divides the Earth into two equal halves horizontally. So now write another note, write axis and then hyphen, and we'll write the definition of axis. An imaginary straight line. Yeah, this is another difference between axis and equator. Equator is not a straight line, it's a kind of a circular line, while axis is a straight line. An imaginary straight line going through the center of the Earth, not center, you can say going through this the center of the poles of the Earth, the center of the poles of the Earth, dividing it into two equal halves vertically, dividing it into two equal halves. And why vertically? Because if it was a complete sphere, then there would be no vertical or horizontal ends to it. But this is not a complete sphere, right? This is slightly flattened at the end, so we can identify its top end and the lower end. And since Earth is in a particular position in the space, so basically we can define which side is the upper side, which side is the lower side. Now, if, imagine you took a ball, so the ball has no upper side, no lower side, right? I mean, if you place it in your hand, then you can mark 2 points on it, right? That this is the upper side, this is the lower side. But if the pole is always in a constant motion, then there would be no upper side or no lower side. But the ball moves in a circular motion, whereas our Earth moves in a slightly tilted and rotative motion. The ball is moving in a revolving motion, but Earth moves in a rotating motion. So that's why we can define its upper side and the lower side. As for axis, I think you've already written what axis is. Now write another note, equator. Write equator and then put hyphen. An imaginary horizontal line, horizontal circular line, an imaginary horizontal circular line running through the center of the Earth, dividing it into two equal halves. Dividing it into two equal halves. Now I've written especially here that it is not a straight line, rather circular. But we've already added it, so there's no need to write it again. So the northern half of the Earth is known as the northern hemisphere, and the southern half is known as the southern hemisphere. So going back to this is our equator, right? And so above this equator, this part is known as the northern hemisphere. This part is the northern hemisphere. And below the equator, that is this part, it is known as the southern hemisphere. So the part below the equator is known as the southern hemisphere, and the part above the equator is known as the northern hemisphere. They are both equal halves. Once again, yeah. Therefore, the equator is an imaginary circular line. Again, they were finally at least they have written a circular line. I mean, I didn't know that the NCERT has also used this particular word, circular line, and it is a very important reference point to locate places on the earth. Now you must be wondering, why do we need this equator, why do we need these north pole, south pole, and all that shit, it's so that we can identify the position of a person or a place or any kind of thing on earth. Earth is really huge, right? But there are cases where people get stuck somewhere, or where we want to locate the position of a building or any country, or any particular event. Let's say that we're talking about Paris Olympics, but we don't know where Paris is, or how do we define where every country is. So we need to locate some reference points on earth, that at this point and this point, the city of Paris is, or the country of US. It's not exactly a country, it's a conglomeration of country, but whatever. Or you can say like USA is at this and this point. So it's basically how you define, like in maths you read about, there was, I don't know, there was Cartesian plane, but it was probably in 11th, so you haven't taken 11th math. But what still there were, there are grid lines. It is similar to grid lines. Like grid lines are always in a cross shape. Let me show you. This, like this floor, these are grid lines. So this point, basically a point like here, like a point here, like these lines are actually the latitudes of the earth's horizontal latitudes, the longitudes, and these lines, there is lines which are, like these are the longitudes of the latitudes, these are the latitudes of the earth. So the straight lines are the longitudes, and the horizontal lines are the latitudes. So in the same way we are dividing this earth. So these, not these, but these lines, and these lines are the latitudes of the earth. Is it latitude? The latitudes of the earth. And these lines, this is one line, and then this is the second line. This whole here is the second line, and this is the third line. These lines are the longitudes of the earth. So this is how we define a point. Like we need to define a point somewhere. Let's say that you need to define a point. This is the point that you need to define. So you would tell which angle is it on the horizontal side, that is which angle is it on the latitude side, and which angle is it on the longitude side. So that way we'll be able to define the position of this uh, point. This is why latitudes and longitudes are important to define the position of the earth, but another important reason as well, to define time, which we'll read later. So first let's see what are parallels of latitudes. All parallel circles from the equator up to the poles are called parallels of latitudes. Latitudes are measured in degrees. So what are parallels of latitude? These circles. I didn't mean to actually select this point as well, but these circles, these circular lines, they are again imaginary lines. So these circular imaginary lines towards either of the poles from the equator towards either of the poles, are known as parallels of latitude. We'll just take our second earth for reference point here. So we know that I'll use a texture paint here to highlight it. So basically this is our equator, this middle line. I'm talking about this middle line, not the colored part, just only the line that this part is coloring. So this is our equator. Okay, then this line here, this line here, and this line here, all these lines, uh, what's happening? Is it my tab fault or this app? So all these lines, and in the same way, these lines that is covering these lines, these are all known as parallels of latitude. So the circular lines, of the imaginary circular lines from the equator towards either of the poles, are known as parallels of latitude. As you can see in this picture here, these markings where they've written 20-degree north, 40-degree north, 60-degree north, 80-degree north. These are imaginary circular lines which are located towards both the poles, towards the north pole, towards the south pole as well, and they are called parallels of latitude because they are parallel to the latitude. The equator represents the 0 degree. Now these are written in degrees, right? So where does this degree start from? There has to be some starting point, right? And that is the equator. So at equator it is 0 degree, and then towards either of the poles it becomes 90 degrees. Why 90 degrees? Let's see why 90 degrees. First let me just color it up back to normal. It's a really hectic process. Now I wish I had a stylus. Okay, so we've just covered it back up, colored it back to normal, mostly. Well, mostly. Okay, so this is your earth, right? Modeling. So this is your earth, and we'll just take this one and then display selected. So we have the second earth is gone. I'll just straighten it up. So for the sake of convenience, I'll just straighten up this earth, and now we'll just select these faces, these lower faces, and then delete them. Here. Oh shit. I think I selected a bit more than I really meant to, but no worries. We'll just do it. Okay, so I've divided this earth into half. So basically this is half earth, right? This is half earth. And you can take this as the northern half or the southern half as well. Let's imagine that this is the northern half. Then if we change it like this, now this becomes the southern half, right? Because they're both exactly the same. So now what we'll do is we'll just cover them up here. What is this shit app? It's just so annoying to use it like this. You must be wondering what I'm trying to do right now, right? Uh, I'm starting to really hate this app now. Well, whatever, just skip this shit. So basically, this is your half earth. And what would be the angle of this half earth, like from here to here, or from like from this point to this point? This, 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 um, to this point to this point, what would be the angle? The angle would be 180-degree, right? Because it is a straight line. But let's say that we need to divide it into further half. Let's say that I'm going to select this half as well and just delete it. Let's say that I'm dividing into actually four equal halves. I'll just delete this area. It's really annoying. I'm just skipping this 3D modeling shit. So let's say that we divide the earth into four equal halves. Okay, now four equal halves. Why four equal halves? Because up to the north pole, from one side up to the north pole, we would cover only 1/4 of the earth. Now, if we let's say that we started on one point of the equator and we go exactly towards the opposite side of that same point on that equator, we go towards the exact opposite side, covering the earth, and we cover half of the earth, right? But we are stopping at the north pole. Let's say that we stop at the north pole, then we cover only 1/4 of the earth. That's why 1/4 of the angle would also be covered by them. That is 90 degree. If you still don't understand, just let's read this. The equator represents the 0 degree latitude since the distance from the equator to either of the poles is 1/4 of a circle round the earth. So if we take a circle around the earth, but if we stop at the equator, we would only cover 1/4 of the earth's distance. So the angle would also be 1/4 of the earth's angle. That is 1/4 of 360 degrees and 90 degrees. Thus 90 degrees north latitude marks the north pole and 90 degrees south latitude marks the south pole. As such, all parallels of the equator are called north latitude. Similarly, all parallels south of the equator are called south latitudes. So all these imaginary circular lines towards the North Pole are called north latitudes, and all these imaginary circular lines towards the South Pole are called south latitudes. And the distance between each line is 1 degree. So there are approximately there are basically 90 lines towards the South Pole and 90 lines towards the North Pole. Okay, and the distance between them is 1 degree. And how would you define? I mean, 1 degree is not basically distance, right? But this does become a distance, when it's actually calculated through the sun's rays. So for each degree the sun's rays shifts, we mark one line. We actually don't need to go into so much detail about this. This is very, very hectic to explain. It's very complex, and I can't really make you imagine every single thing about it. So you just try to remember this. So the value of each latitude is therefore followed by either the word north or south, because basically the angles on both the latitudes are same. So if you don't define which side we're talking about, we'd never know which latitude you're talking about, right? Let's say that I only said 20 degrees. So now you don't know which 20 degree towards the south side or 20 degree towards the north side. So you have to add this symbol N or S to define which 20 degree you're talking about. Which 20 degree latitude you're saying, 20 degree latitude towards the north or 20 degree latitude towards the south. Important parallels of latitude. So you need to make notes of these and you need to remember them exactly, like completely exactly. So just write down equator is equal to 0 degree, and then write down Tropic of Cancer is equal to 23.5 degrees north. North is important now. This is again. Then write down another one. Tropic of Capricorn is equal to 23.5 degrees south. Then write Arctic Circle is equal to 66.5 degrees north. Antarctic Circle is equal to 66.5 degrees south. You need to remember these exactly with their angles. Now let's talk about the heat zones of the Earth. So torrid zone, what's a torrid zone? A torrid zone is an area surrounding the equator which receives maximum heat and direct sunlight, typically in between Tropic of Cancer and Tropic of Capricorn. So as you can see here, this area is the torrid zone, and it is nearby the equator, and it is mostly it is by, like in this picture, it is completely between Tropic of Cancer and Tropic of Capricorn. So in short, you can also say that the area between Tropic of Cancer and Tropic of Capricorn is known as the torrid zone. Okay, or basically between 23 degree north and 23 degree south. The area between 23 degree north latitude and 23 degree south latitude is known as torrid zone. Why is it called the torrid zone, and why is it important? Because this is the area which receives maximum heat on Earth. So this is basically the hottest area on Earth, or where the sunlight and the heat is maximum, because the sun's rays fall directly on it, directly, like at a 90-degree angle, they fall directly over it. So this is the torrid zone. For this definition, you can write torrid zone, then hyphen, area surrounding the equator, comma, which receives maximum heat and direct sunlight, comma, typically in between Tropic of Cancer and Tropic of Capricorn. So now you know what torrid zone is. Moving on towards temperate zones. What are temperate zones? Now, one thing to note here is that before it was only torrid zone, but now this is temperate zones. So there is more than one. There are zones. So temperate zones, areas which never received that. Now I'm telling you to make a note of this. Write down this note. Temperate zones hyphen areas which never receive direct sunlight and therefore have moderate temperatures. Areas which never receive direct sunlight and therefore have moderate temperatures. These areas are between Arctic Circle and the Tropic of Cancer in the northern hemisphere. These areas are between the Arctic Circle and the Tropic of Cancer in the northern hemisphere, and the Tropic of Capricorn and Antarctic Circle in the southern hemisphere. And the Tropic of Capricorn and Antarctic Circle in the southern hemisphere. So we'll just look at this Earth. So this is the here. This is the north temperate zone between 23.5 degrees north to 66.5 degrees north. And this is the south temperate zone between 23.5 degrees south to 66.5 degrees south. So now you remember why it was so important to remember all these different points, these different angles, this Tropic of Capricorn, Arctic Circle, and Arctic Circle, because they come in handy now. So torrid zone, temperate zone, moving on to frigid zones. Now frigid zones are really cold because the Earth rays, they yeah, in the temperate zones also you need to remember one thing, that the midday sun, that is the sun during the during near about the middle of the day, like somewhere around 12 p.m. or between 12 to 1 p.m., something around that time. The sun does not shine exactly at a 90-degree. The sun is never at a 90-degree angle at these points. Like if you're living in India or China or some of these countries, there is one point during the day at which the sun comes exactly overhead, like exactly forming a 90-degree angle with your head. It is exactly above your head. But in these areas, the sun is never exactly above your head. It is always slightly slanted. So the sun's rays are always slanting in these areas. They never shine exactly overhead. And for the frigid zones, areas lying between, so it is here the sun does not rise much above the horizon. Its rays are always slanting and provides less heat. So these areas are basically cold throughout the year. Okay, they're cold throughout the year. This is the frigid zone. It is between the Arctic Circle and the North Pole in the northern hemisphere. In the southern hemisphere, it is between the Antarctic Circle and the South Pole. So these areas are very cold and basically covered in ice throughout the year. The sun is always, on the horizon. Like it all, if you are living in these areas, you will always see the sun at a position where it's, like setting. So if you look at from India, so the point where the sun seems to be setting, it remains at that point in these frigid zones. Whether the sun is just rising or whether it is setting, it is basically at the same point. To understand it more effectively, you can just go to YouTube and search for frigid zone sunset or frigid zone sunrise, and there you would see how much the sun seems to rise above the Earth's surface. Like to give you an idea, we can basically, I think, open up YouTube and see it for ourselves. Frigid zone sunrise. Here, this is the frigid zone sunrise. Yeah, this would explain to you very effectively.
How can this be in the middle of the day, and why do we have 4 months of darkness? My name is Cecilia and I live on Svalbard, an island close to the north. How can this be in the middle of the day, and why do we have 4 months of darkness? My name is Cecilia and I live on Svalbard, an island close to the North Pole. The Earth rotates on a tilted axis. And due to our location being so far north, we are tilted away from the sun. Because of this tilt, the sun doesn't rise here for 4 months. And for 2.5 of those months, the sun is more than 6 degrees below the horizon, which means that no light reaches us at all. Which leaves us in a very dark polar night where we have no light whatsoever 24/7 for 2.5 months. Do you think you could live like this? I personally love it. Okay, bye.
So basically, you saw how the Earth does not, how the sun does not really rise much above the horizon. Basically these are areas are almost always covered in darkness, and there's not much sunlight even when the sun is up there. Even when the sun is in the sky, there's not much light, and it's basically, still dark there. So these are the frigid zones. Now, what are longitudes? Now, longitudes are again a big headache, just like the latitudes. So the longitudes are basically these vertical lines in which the Earth is covered. Again, these are imaginary lines. Remember, these longitudes and latitudes are both imaginary lines. So whenever I speak of lines, the next time I say lines, just remember that I'm talking about these imaginary lines. So longitudes are basically the lines which cover the Earth from in a east and west direction. Previously, the latitudes covered them in a north and south direction, right? But longitudes cover them in a east and west direction. So that's why they are vertical lines. Those were horizontal lines, and these are the vertical lines. Vertical but circular lines, circular and vertical lines. So to put down a heading for longitudes, you can just write imaginary circular vertical lines that cover the Earth, where latitudes run from equator towards north and south poles, longitudes move in the direction of east and west. Okay, so we're contrasting them from contrasting them with uh, latitudes as well, how they're different from latitudes. There are a few more differences between latitudes and longitudes. Since the Earth is spherical, now this is only for convenience sake. We know the Earth is not spherical, but just for convenience sake, we're just saying that the Earth is spherical. So I'm saying that since the Earth is spherical, its its horizontal length is the largest at the equator, successively decreasing as you move towards the. So basically, what I'm trying to say here is that let's imagine this is our, this is actually kind of our ruined Earth. So we'll just create a new Earth. So this is our new Earth. Okay, let's create it a big. So you will notice that if this is the equator, this is the equator. Okay, basically this is the equatorial line, right? But as we move towards the pole, this line, these lines, these parallels of latitude, they start decreasing in size, right? You can say that they start decreasing as the equator, the parallel at the equatorial line is the largest. Then as we move towards the pole, the lines become successively small, right? But in the case of this, in the case of these longitudes, in the case of longitudes, the lines are of equal length. All the lines are of equal length. See, all these lines are of exactly the equal length. They do not keep on decreasing like in the, as you can see, the first line is the largest and the second line is smaller, then the third line is even smaller, and as we move towards these points, these lines would become even smaller. I mean, I've chosen a wrong point, but you will see that these lines would become smaller and smaller, right? But in the case of the longitudes, these lines would remain basically remain the same. So their length would remain the same. So this is another difference between latitudes and longitudes. Since the form of vertical part of the spherical Earth and the sphere is equal from all sides in a vertical manner. Yeah, the sphere is equal in from all sides in a vertical manner, right? The longitudes, just like latitudes, are divided into degrees, but unlike the maximum angle of the latitudes being 90 degrees, the maximum angle of longitudes can be 180 degrees. So the maximum angle of the longitudes is 180 degrees. What was the maximum angle of the latitudes? It was 90 degree at the North Pole, right? But in this case, the maximum angle of the longitudes is 180 degrees. So they move 180 degrees towards the west and they move 180 degrees towards the east as well. Okay, like 180 degrees towards east and 180 degree towards west. So we're moving on. Now we'll see how they. So basically, these longitudes and latitudes divides the Earth into four different directions. The longitudes do the work of dividing the earth into east and west, whereas the latitudes do the work of dividing the earth into north and south. So that is why we need to put these imaginary lines, so that we can mark the positions on earth. Now, since we have a baseline in the case of latitudes, right? And the baseline is called equator, from where all the angles are measured. So in the case of latitudes also, there must be a baseline from where all these 180-degree angles are measured towards the east or south. That baseline is called the prime meridian, and again it is at the center of the earth, in a vertical center of the earth. So if we take the earth to be in a vertical position, then the exact center which would divide the earth into, basically it is parallel to the axis. So the angle parallel to the axis is that imaginary line is basically our prime meridian. Here you can see this is our prime meridian, and it is parallel to the axis of the earth. And from here we measure different angles, 180-degree angle towards either of the sides. Now there is another important job of prime meridian, and it does the work of, it does the work of telling us the time on earth. This is what we use to measure time. Now just a little break. Well, okay, so this is how I'm going to explain to you the concept of prime meridian and timekeeping. So let's imagine that this is your earth, and this straight line is the line of prime meridian, and this here is sun, and the sun's rays, I'll just show you, are falling at an exact straight line. Okay, so sun's rays are falling directly on this prime meridian. So at this point of time, the time on Earth is exactly, it's exactly 0. Come on, man, the dots 0 0. Okay, this is the time on the time on Earth as of now. Hey, why isn't the pen working? So this is the time on Earth right now, 0 hours and 0 minutes, when the sun's rays are falling directly on the surface of the Earth. But for every second, let's say that the Earth's rays are, let's take this point. This point. Mm, Let us take this to be the point that the sun's rays are falling on Earth directly at. Now, for every degree that this point shifts, let's say that this point shifts towards this area, and then it shifts towards this point. Man, this is annoying. This is seriously annoying. I cannot draw a point on it. Okay, now this shifts to this area, and then this area, and then this point, and then this point, and this point. And so, because the Earth is rotating, okay, the Earth is basically rotating, so I can't actually exactly show you in a 3D motion. But let's say that the Earth is rotating, and then the sun's rays are shifting to these points. The direct area. The sun's rays then falls directly on this part, and then after some time falls directly on this part, and then falls directly on this part, and this part, and this part, and this part, and so on. It falls on each angle on the Earth's surface. But for each angle that the sun's rays shift, okay, for each angle of Earth's rotation and the shifting of the sun's direct rays, 1 hour is taken to have convened, 1 hour is taken to have passed. So it takes, or in another sense, you can simply say that it takes 1 hour for the sun's rays to shift directly, or for the direct, for the direct sun rays to shift by an angle by 1 degree. So this is prime meridian, where the angle is what? Where the angle is 0 degree, right? So at 0 degree, there is 0 hours and 0 minutes. But if the sun's rays start falling directly on 1 degree instead of 0 degree longitude, then it means that 1 hour has passed. All right. Now, if the sun's rays shifts again and falls directly on 2 degrees, then it means that 2 hours have passed. Going in the same way, when the sun's direct rays shift from 2 degree to 3 degrees, then it means 3 hours have passed. If it shifts to 4 degree, then it means that 4 hours have passed. So in the same way, there are actually, there's if because there's a kind of 360-degree rotation hole. So Earth basically Earth has 360 hours, right? Earth basically has 360 hours. So it takes 360 hours for the Earth to reach that same point from where it had started. For the Earth's rays to fall directly on the prime meridian again. This is actually quite complex to explain, again, because if this was the case, then it would mean that it would be kind of like, like it would take almost 360 hours for in a day. But no, this is not the case. But since, because the areas on the Earth, the countries have very large area, very wide area, and then sun's rays are not like this. Let me erase it. So sunlight or sun's rays do not form a direct line, okay, like I've shown in this one. They do not form an exact line like this, but instead they cover a large area, okay, they cover this large area, they fall on a large area. And that is why we're able to cover this span of 360 hours in a mere 24 hours. So you can basically say that it does not fall exactly on a straight line, rather it covers a lot more area of the Earth. But the thing is still that when it is falling on this prime meridian, we take that time to be we take that time to be 0 hours and 0 degrees. And for every hour, take that 1 degree has shifted, or the sun's rays has shifted by a degree. So that is why basically this is divided into degrees, that 1 degree, let me actually just check it, give me a second. Okay, so I just checked it and I actually made a huge mistake here. This you can do, just clear up this concept of 360 hours covered in 24 minutes. I actually made a mistake here. I'm really sorry for that, really, really sorry. It was a huge mistake. So everything, up to this point is fine. This is our prime meridian, and the earth and the sun's rays are falling directly on the prime meridian. But it does not take the sun 1 hour. It does not, it does not take for the sun's rays to shift by 1 degree. It does not take 1 hour for the sun's rays to shift by 1 degree. Instead, it takes only 4 minutes. It takes only 4 minutes. So in every 4 minutes, the sun's direct rays, okay, I'm talking about the direct rays, the sun's direct rays shift by 1 degree angle. So it will basically take, how many minutes, like there is 360 and then 360 into 4, and then it would be 1460 minutes divided by 24. So it should basically take 60 days for the sun to complete a revolve and then come back to its position. But this movement is faster because the earth is rotating in that same time as well. So due to the rotation, we cover this time period faster. So actually what I'm trying to say here is that for every degree shift of the sun's rays on the earth's surface, for every degree shift, 4 minutes are passed. Okay, so let's say that the sun's rays are at this point, which is prime meridian. So it is in the at the center of the earth, and slowly they started shifting towards India. And at India now, it is sunrise in India because the sun's rays are starting to light up this country. And let's say that this country is about, let's say that if the prime meridian is at 0 degrees, then India is at, just imagine, just for imagination's sake, let's say that that India is at 42 degrees east. Okay, so we know that for every degree, 4 minutes seems to 4 minutes are taken to have elapsed. So now the sun's rays have shifted by how many degrees from prime meridian? 42 degrees. So how many minutes have passed from the Earth's time, or from the time at Greenwich? So how many degrees will you? How many minutes or how much time do you think have passed on Earth from Greenwich? We'll take Greenwich as a reference point because Greenwich is the area, is the place from where the prime meridian passes. So you have to do nothing. You just multiply 42 by 2. Just multiply 42 by 4, and it would give you 168. So it basically 168 minutes are passed. If you divide it by 60, then it would give you something about 2 and a little more hours. No, yeah, 2.7 hours something. 2.8 hours exactly. So 2.8 hours. So India's time is 2.8 hours ahead of the prime meridian's time. Okay, like the prime meridian's time. But the earth is revolving really fast, so it covers this much time period. And so 1 degree, and then 1 degree here, and then if it's revolving like that, it should take around, how many, it would be covering 180 degrees and then 180 degrees, and for every 360 degrees it would take 360 degrees into 4 minutes. We need to stop it for one. Okay, so now I understand it. I was actually, making a mistake in my own calculation. No, I did not tell you anything by mistake this time. I just made a mistake in my own calculation. So what I'm trying to basically say here is that the sun's rays, let's take that the sun's rays are actually doing a journey. Okay, let's try to understand it in this way, that the Earth, not the Earth this time, but the sun's rays are on a journey. They're on a journey. Now, this is an adventure. Okay? This is an adventure, but it does not include any risks or any life-threatening situation. So, this is the starting point of that adventure. This prime meridian, the center of the Earth. This is the center of their adventure. And then they travel this side. The Earth is rotating, and they're covering the Earth. They're actually kind of covering the Earth because the Earth is rotating. So the sun's rays are kind of covering the whole Earth, and for covering each degree. since the Earth is rotating, and in rotation, the Earth is rotating at a particular angle, right? The Earth is rotating at a particular angle, and for each degree that they cover, they take about 4 minutes. Okay, let's say they take about 4 minutes, and we know that the horizontal, that the Earth's latitudes, sorry, longitudes, that the Earth's longitudes, if if joined together, they form a complete angle of 360 degrees, right? 360 degrees. So how much time would it take for these sun's rays to cover the entire Earth once? Okay, to go circle around the entire Earth once, because the Earth is divided into basically 360 degrees. So they will have to cover the entire Earth, they will have to move 360 degrees, right? And for each degree, they take 4 minutes. So they would take 360 degree into 4 minutes for covering the entire Earth. Now this would give us 1440 minutes. Now to convert it into hours, simply divide it by 60. Okay, this would give us 24 hours. So this is why one day takes about 24 hours. Okay, I told you the exact time of a day is basically 23 hours and 56 minutes, and this is because it does not take exactly 4 minutes to for the sun's rays to cover 1 degree. It takes, if I tell you the exact time to cover, they haven't given the exact time. So they're always there everywhere. They're just saying, that it takes 4 minutes, 4 minutes, but obviously it cannot take exactly 4 minutes, because the Earth, basically the number of hours and minutes in a day is basically 23 hours, 56 minutes, and 4.09 seconds. Okay, so if we add up all this, so 23 hours would give us 1380 hours, 80 minutes, sorry, not hours, 1380 minutes, plus we add the 56 minutes as well. So it would give us 1436 minutes. So 1436 minutes. So it basically takes 1436 minutes for the sun's rays to cover the entire Earth, to pass through. You can say to pass through, because when they're passing through a particular area, then the other area is obviously in darkness, or there is night there. That's why I said that it would be really complex to explain, because it's really hectic and I can't create any 3D motion either. So basically, let's imagine that this is the part where the Earth's rays are falling. The Earth is rotating and this side is towards the Earth. So basically, this part of the area is where there is day. So obviously, on the whole other part of the Earth, there is night, right? And this part now shifts now, because the Earth is constantly rotating. So now it shifts towards this part. So we can say that the sun's rays have covered from here to here, and then next they cover from here to here, and in the next some time they cover from here to here, and then here to here and here, until they reach this original point from where they have started by covering up the whole Earth. This covering up the whole Earth, they eventually reach this point. Okay. So in this way, they'll have to cover 360 degrees, and we know that for each degree they take about 4 minutes of time. So they take about 1440 minutes for covering each and every degree on the Earth, which would conclude to 24 hours. But we know that a day does not have exactly 24 hours; it has 23 hours and 56 minutes. So we'll go the other way around. We'll just take first we'll calculate the number of minutes that it should take, and now divided it by the number of degrees. So divided by the number of degrees. So it basically takes the Earth. It basically takes the sun's rays 3.98 seconds. Okay, not exactly 4 minutes. Sorry, not seconds. Sorry, minutes. It takes 3.98 minutes, or maybe it can go by about something like 97. So basically 3.98 or 97 minutes for the sun's rays to cover 1 degree exactly. Okay, now this is why longitudes are important, because for each degree of longitude covered by the sun's rays, 3.97 minutes are taken to have passed, or to put it approximately 4 minutes are taken to have passed. So let's say that the Earth started on prime meridian. At this time, there is 0 minutes, 0 hours, 0 minutes, and it covers a degree of, and the sun's rays have shifted by about 10 degrees from the prime meridian. Now the sun's rays have shifted by about 10 degrees towards the east, because the sun rises, because the Earth moves from west to east, right? From west towards east. So let's say that now the sun's rays have shifted by 10 degrees. So how much time has passed on Earth? So just 10 degrees into 4 minutes, so basically 40 minutes. So 40 minutes have passed on Earth. Simple as that. Okay, like they haven't even explained it anywhere. So the best means of measuring time is by the movement of the Earth, the Moon, and the planets. The sun regularly rises and sets every day. Naturally, it is the best timekeeper throughout the world. Local time can be reckoned by the shadow cast by the sun, which is the shortest at noon and longest at sunrise and sunset. So here they are saying that when the prime meridian of Greenwich has the sun at the highest point in the sky, that is basically when the sun's rays are falling directly on it. All the places along this meridian will have midday or noon. As the Earth rotates from west to east, those places east of Greenwich will be ahead of Greenwich time, and those to the west will be behind it. The rate of difference can be calculated as follows. The Earth rotates 360 degrees. Yeah, so this is basically, now this they will help you understand better. So basically the Earth covers about 360 degrees of rotation in one day, right? And one day has how many hours? 24 hours, which means that it covers about 15 degrees in an hour, or about 1 degree in 4 minutes. Okay, it covers about 1 degree in 4 minutes. Thus, when it is 12 noon at Greenwich, the time at 15 degree east of Greenwich, east means ahead of Greenwich, will be 15 into 4 is equal to 60 minutes. That is 1 hour ahead of Greenwich. So it would be 1 hour more than Greenwich. Which means it will be 1 p.m. 1 p.m. because at that time it will be 12 p.m. at Greenwich. You know, when the sun is exactly overhead. When we talk about when the sun is exactly overhead at Greenwich, then it is 12 p.m. at Greenwich. If the sun has just risen in Greenwich, then we can conclude that only their time has only just started. You know, so basically, because each country has its own timeline also, so that's why this has become so much messy, you know, because the Earth has its rotating time, and then each country has its rotating time, and then from Greenwich we have to check the world standard time as well. So that's why this is all messy. So, but basically, you get the idea what I'm trying to say here is. So basically, what we're saying here is that now it's going to take all day to open. This is why I hate Microsoft my whiteboard. The only reason for it. Well, whatever. Yeah. So here, so here you have your Earth, full of glitches, and nothing. It's not erasing shit. See, it's not erasing shit. Well, whatever. But I was trying to say here that this is your Earth. What the heck? Forget. Goodbye to Microsoft Whiteboard. So basically, just say that this at 60-degree east. So yeah, you tell me, guys, now. This is our Indian map, and this here, this starting point is 68-degree east. So how much time has passed from Greenwich time? We're taking Greenwich time, or which is the prime meridian, as the starting point. So how much time has passed on Earth when the sun's rays reaches the starting point of India? How much time has passed by then? We have given you here that this is 68-degree east. So you need to calculate the time now. So you have about 10 seconds. Tell me. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So this is very, very easy. You just need to do nothing. You just need to take 68, because you know we know that that this area is 68 degrees ahead of the prime meridian, which is 0 degrees. So at 0 degrees, the time is obviously 0000, right? But at this point, it will be 68 into 4. That is 272 minutes. Now divide 272 minutes into by 60 to convert it into hours. So this is 4.5 hours. So 4.5 hours have elapsed on Earth. Okay, if we're talking about Earth as a whole, we're not talking about specifically Greenwich. We're talking about Earth as a whole. So as a whole, on Earth, 4.5 hours have passed. And in other words, as well, we can say that the time in India is 4.5 hours ahead of Greenwich. So if it's 12 p.m. in Greenwich, then it would be 4 p.m. and 33 minutes in India. So here, but at any place, a watch can be adjusted to read 12 o'clock when the sun is at the highest point in the sky. That is when it is midday. The time shown by such a watch will give the local time for that place. You can see that all the places on a given meridian of longitude have all the same local time. Yeah, so this is obvious. So like all of these places, say if you take this, now this is like deleted, again this is like, let's say that this is your Earth and this is that longitude. So all the countries on this particular longitude, on this particular line, okay, all the countries on this particular line will have the exact same time. Okay, they will have the exact same time. Well, of course, unless they have their different standard time, because each country has their different standard time as well. But according to the Earth time or according to the world clock, these countries would have the exact same time. Because the earth rays falls on this complete area at the same time, right? It's not like the earth's rays fall in a slanting manner, like not in a slanting manner, I'm saying. It's not like the earth rays are falling on this area. Hey, what the heck? That on this area the earth rays are falling like this, and then on this area it starts falling like this, and on this area it starts falling like this. The sun's rays falls in a straight line in this straight manner, right? So it would fall on a particular place at the same time, and each countries would all have the same time. But we all know that even on the same plane, even on the same longitude, each country has different time. Why is that? Because each country has their own standard time. Now, what is standard time? The local time of places which are on different meridians are bound to differ. For example, it will be difficult to prepare a timetable for trains which cross several longitudes. Okay, because since most of the countries are very wide, they are very big, so they have several longitudes within them. Like India, India has from longitude 68 degree east to 97 degree east. So how much longitude does India have? So it would be simple, 97 minus 68, which gives us 29. So India basically concludes or holds within itself 29 longitudes or 29 longitudinal lines. Now we know that on each line there is a shift in degrees, right? There is a shift on degrees, but we conclude one central point, that we will take this central point to be our what? To be our standard time. Okay, to be our standard time. So basically let's just imagine that the sun's rays starts falling on 68 degrees east, and by the time they reach let's say 82 degrees east, it is starting to be dark at 68 degrees east. So in this way they will set up their own time. Okay, they will set their own time. No, this will our time will be different. But on the whole in the whole of the country, we have a standard time. We have a standard meridian. It's similar to prime meridian, but now we're taking, instead of the earth, we're taking India, and we take a line to go to the center of our country, an imaginary line again. And this is what we conclude the center point, and this will be the center point from where we will take our time. For example, it will be difficult to prepare a timetable for trains which cross several longitudes. In India, for instance, there will be a difference of about 1 hour and 45 minutes in the local times at Dwarka. Because let's say that we take what do I say? So basically, what we're saying is that this is our standard time, and this is the like similar to prime meridian. This is the time that all of the country has to follow. It is therefore necessary to adopt the local time of some central meridian of a country as the standard time of the country. In India, the longitude of, now remember this one, this is your point. The longitude of 82.5 degree east is treated as the standard meridian. The local time at this meridian is taken as the standard time for the whole country. So the time that is at this point, that is at the center, that is at the standard meridian, is taken to be the time that is in the whole of the country, in all of the country. It is known as the Indian Standard Time. Okay, so basically this was it. Now I know this was a really tough chapter, and probably many of you did not understand many things. So you can just, you can just go through this chapter. You can just go through the video and read this book yourself, and that will clear half of your doubt. But if you still have doubts, you can, just write it down in the comments, and I'll try to explain as best as I can. This whole time thing, you don't need to remember everything about it. You just need to remember few things, a few major things, which are what, that for each degree of longitude, it takes 4 minutes. Okay, like every it takes, or you can just simply say it as that it takes 4 minutes to cover 1 degree longitude. So if we cover 10 degree longitude, then it means that we took 40 minutes. If we cover 5 degree longitudes, then it means we covered 50 minutes. If we covered 6 degree longitudes, then it means, sorry, what am I saying, 60, 50 minutes, sorry, so let's start again. If it takes 4 minutes, so for each degree it takes 4 minutes. So let's say if we cover 5 degree longitudes, then it will take 5 into 4, that is 20 minutes. If we cover 10 degree longitudes, then it will take 10 into 4, 40 minutes. Okay, this is how it works, and it depends on the sun's rays. The sun's rays fall directly on the prime meridian. At this time, the time is 00, no, if it's falling directly on the prime meridian, then at that time the time is basically 12 p.m. The time is 12 p.m. The time will be 00 if the sun's rays have just started, only just started to reach the prime meridian. So without, all those necessary softwares and all that stuff, it was really hard to explain. But still, this is, just basic stuff. You don't need to go into too much detail about that. You just need to have a basic idea of what it all means. So we'll see you in the next video, and until then, goodbye and take care.